All right, so this is a video that was lost and a student asked about it, so I'm just recreating it. I want you to consider the situation in which we are going to see what the flux is through a rectangular loop that is close to a current carrying wire. And then we're going to consider two situations. One situation in which the current in that wire is changing, thus triggering a current to be induced in the loop. And one situation in which the loop itself is moving in this field, thus also triggering a current in the loop. So what I've done is I've frozen a moment in time. So let's get this whole thing out of here because we don't need that right now. Let's just consider that there is a current in the wire that is this direction. Because for the first part of Faraday's law, we are trying to calculate the magnetic flux, and in calculating the magnetic flux, we just need to freeze a moment to have an understanding of how much magnetic field is passing through the area of our wire loops. Now, I've drawn these X's on the side to represent the direction of the magnetic field. And of course, let me make sure I have my current going in the right direction to actually create that magnetic field. The magnetic field would be into the page, above the wire, and out of the page, below the wire. But because our magnetic field is from a current carrying wire, the size of that magnetic field is based on the size of the current and how far away from the wire we are, so the perpendicular distance away from the wire. So as I've drawn here, the magnetic field is very concentrated in a region of space close to the wire, but the magnetic field becomes smaller and smaller as I move away from the wire in an inverse relationship. So in this loop, which is near the magnetic field, which is near the wire, so it's within the magnetic field of the wire, the amount of magnetic field or the strength of the magnetic field in a region of the loop, say here, is different than the strength of the magnetic field in the region of the loop, say up there, because the magnetic field is getting weaker. So this is an example where when we go to calculate the flux in the loop, that our flux is going to be based on, of course, the size of the area, and the direction of the magnetic field, and the direction of the loop, but also the strength of the magnetic field. But the magnetic field isn't the same throughout the entire area. So unlike other examples where we've been able to kind of pull the magnetic field outside of our summation, we're not going to be able to do so this time, because for every single different area inside this loop, there's a different strength magnetic field. Thus, it contributes differently to the total flux. So in order to do this integral, we are going to count on some symmetry. So what I'm going to do is I'm going to highlight an area in the loop. And I'm just picking a random location, a random area in this loop. So this red rectangle is one of the area. I like to write that as, say, DA, a piece of the area. Now, this particular piece of area needs some parameters. First, I think we can agree that it is W wide, because it's going to be the same width as the rectangle since it's kind of aligned to my wire. However, as an area goes, it's length times width. So I need some variable I can use to kind of express how wide my loop is. So I'm going to, just for consistency's sake, in this example, I'm going to call this width right here dr. And I'm going to say that the start to this area is located R away from my current carrying wire. Now, I want you to think about this for just a minute. R is going to start here, That's where the first piece of area will be. So you have to imagine that there is an area here that will be considered, and this area will have the strongest magnetic field. And our area is going to end here. And of course, you have to imagine that there is an area here as well that will be contributing to the flux, but it's going to have the weakest magnetic field in the loop. And every single area in between will have a different amount of flux, or a different contribution to the total flux, as the magnetic field is decreasing throughout the entire loop. So let's get all that out of the way because I don't need it. And there we go. So I'm going to state right now that the piece of area is the product of the width of the loop times dr, which is the length of the loop, or at least it's along the side where the length is. This is an area, and I'm going to use it to replace the area in my integral. But before I do that, I also need to come to grips with the fact that the area has direction. I mean, there's a dot product. Because the area has direction, I need to kind of convince myself that I understand the relationship between the direction of the area and the direction of the magnetic field. Now, this isn't a closed and bounded surface, so I know that my direction of the magnetic field is into the page. I can, at the same time, state that my area is also perpendicular to the page. It could be either perpendicular in or perpendicular out. That's for my choosing. It's going to make the flux either positive or negative. That part is immaterial. I just know that the angle between the area and the magnetic field is 0 degrees. So I can make my first kind of substitution, and that is replace dot product cosine, knowing that my magnetic field and my area are aligned. The next replacement is to replace the area with my expression for the area that is now based on how big each piece of area is in terms of r, which is just a little bit in the r direction. Now, my goal is to be able to sum up all the contributions, but I need to put in here the fact that the magnetic field is different for one r versus a different r. That's the whole point here. So I'm going to substitute in an expression for the magnetic field, u naught I over 2 pi r times w times dr. Now, it's right about this moment that I take a brief aside to remind my students that we are taking a snapshot, a moment in time. Our current might be changing. If it is changing, we might have something that we will substitute in for the current. But our magnetic field isn't changing with respect to time right now. It's changing with respect to position right now. We have frozen a moment in time. So this expression that I just pulled out from above the screen tells me that the current in this loop might be changing with respect to time, and that would change the magnetic field, but only when I'm taking an integral or a derivative with respect to time. I'm taking an integral with respect to position. So for an instant in time, any momentary instant, the magnetic field is changing, but it's changing with respect to position r. We'll deal with time later, so I can leave a placeholder in I. Now, should we be talking about the situation in which the loop is moving? Well, that would mean that our starting distance here, that starting distance, that would be changing. And our ending distance would be changing. But for this moment in time, we're just going to say that my particular loop starts at a position, and I'm just going to give a placeholder variable here, A. I'm starting with my loop at distance A away from my magnetic field. Away from my current carrying wire. So let's go ahead and finish off our integral. And going to bring it down here, but now I'm going to start adding some stuff to my integral and start identifying which things are actually a part of the integration process and which things are going to be the same for all terms in my integration. So first, I'm going to start at distance A. That's where my first R is. My first piece of area will start a distance A away, and I just made up that placeholder just now, so I would have a parameter there. And I'm going to end a distance A plus L because the entire loop has a length of L. Now, I'm going to go through this and write out each of these, but anything that is going to be the same for every single R, I'm going to write in green. So mu naught is the same for everything in R. I is the same. It does not depend on R. 2 pi does not depend on R. W does not depend on R. And what's left is R, that depends on R, and my integration variable dr, which is telling me to take this integral with respect to R. All righty. We can ignore the setup now. We are looking just at the math of this. I'm going to pull out every term or every portion of this expression that has nothing to do with R. And now I'm left with an integral from A to A plus L of 1 over R dr. This is a straightforward integral. So now that I'm working on my integration part, I'm going to take the antiderivative of 1 over R, get the natural log of, because I should be consistent with my color coding, the natural log of R evaluated from A to A plus L, which is going to give me mu naught I W over 2 pi, and now I'll have the natural log of, I don't care that it's all in green now, A plus L over A. This will be the expression I'm going to use for flux. Now, if none of it's changing, there is no EMF produced. But if any of it is changing, then an EMF might be produced. So the things that are likely to change could be an expression for I or something about A. Either of those could work. So let's consider how we might go forward here. Let's talk about a situation in which we have an expression for the current. All right, so now we have the different conditions. We have our flux. So let's consider the situation in which our current is not constant. So I suggested this, a situation in which our current is changing. This is showing a current that is decaying over time. Now, this is going to bring up two things that we have to deal with. We're going to have to deal with the fact that there is an expression for the EMF that is produced. We're also going to have to deal with Lenz's law, which would be the direction that that the current would be in this loop. All right, a quick cleanup, move all that over to give me a little space. A reminder that this is my expression for the flux. I'm going to leave it right up there. And now Faraday's law. Faraday's law says that an EMF will be produced when there is any change in flux with respect to time. So if you change the flux while the loop is sitting there, you're going to get an EMF produced. That could be changing the magnetic field by changing the current. That could be changing the angle that the loop makes with respect to that magnetic field. Or it could be just moving the loop inside the region of space where there is a magnetic field if that changes the size of the magnetic field. We're going to do the case where our current is changing. Now, the negative sign is a holdover from Lenz's law. And although the negative sign is real and does give us a negative or a positive answer depending on what happens with our derivative, it's important to note that Lenz's law can be figured out using a different method. And so the method I want you to consider is we currently have a magnetic field that universally is into the page here, or into the screen. But our current is getting smaller, and the magnetic field portion of our current magnetic flux portion of our current is dependent on I, and I is getting smaller. So the magnetic field in this region of space is decaying because the current is decaying. Because the current is getting smaller, the direction of the EMF that's going to be produced in the loop has to be to generate a current that will try and maintain the state of the flux. It opposes a change in flux. So there needs to be a current created that is in the direction of the magnetic field because the magnetic field is going away. Using my right-hand rule, that suggests that the current that will be produced in the loop is going to be clockwise to try and produce a magnetic field in the same direction as the current magnetic field, since the current magnetic field is going away. There. We've handled the direction of the current that's going to be produced in the loop. Now let's find the value for the EMF. First, I'm going to go ahead and drop the N and drop the negative sign because both of those are handled. There's one loop and we handled the direction of our current. So we're looking at the rate of change with respect to time of mu naught. Now I'm not going to put I there. I'm going to put what I have for my expression for I. But for the moment, I'm just going to leave it blank, put all the other pieces that are here. Now, my expression for the current starts with some current I naught and is a decaying exponential. So, first thing I want to look at is recognize that the only thing that matters here is anything that changes with respect to time. So that's just this. It's the only thing that changes with respect to time. Everything else is a constant. So before I even start doing any real math here, everything that is staying the same, that is not going to change with respect to time, should be pulled out from my derivative. And all that I will have left is the rate of change of e to the negative beta t. Now, all I have to do is take the derivative of that part. So that means my EMF will be equal to all of this. And when I take the derivative of that exponential, I will get back the exponential. But I'm also going to get, due to the chain rule, a negative beta. I'm going to put the beta up here for sure. And I'm going to put my natural log. I can put my e to the negative beta t right there. And that's the result of taking the derivative. Now, consider this. The negative sign that was here would have canceled out with the negative sign for this. I'm telling you that there's an EMF, but that doesn't really tell you the direction of the EMF. It could be stated that because the EMF was positive during this process, that it suggests that the direction of the current would be to maintain the direction of the current magnetic field to the loop, not to oppose it. But I think it's still best to employ Lenz's law secondary to your process. Now, we could move the loop. We could say that the loop is traveling with some speed this way, which would mean that its velocity would be related to dA dt. That would mean that suddenly when we go to take the derivative, if our current was constant, this would become the focal point of our derivative. But tell you what, I've done enough for today. You try it.